Now, as we look at this differential equation, we see that it is not separable, as we can't separate both the x terms and the y terms to one side or the other, and it is not linear. Okay. We see first we have a y raised to a power other than 1, so that's our first giveaway, it's not linear. And additionally, we see a product of y and its derivative, so it's not linear and it's not separable. But one thing that we do notice in terms of a classification is that the combined powers are all equal. For instance, we have an implied power of 1 for the x, 1 for the y. Combined, that's a power of 2 for this term. We see this term is squared, also a combined power of 2, and this is a combined power of 2. So we know from that that we're looking at a homogeneous equation. And in order to solve this, we'll want to isolate our y prime term. So let's divide both sides by our 2xy, and we get dy dx equals x squared over 2xy plus 2y squared over 2xy, and then we can simplify the right side. And once we've recognized this is a homogeneous equation, we have a substitution that we generally use. Let's let the variable v be equal to the expression y divided by x. This could be rearranged to match this term. V to the negative 1 is x over y. Now, as we go about this substitution, we see that y over x for v could be replaced here. Our v to the negative 1 is the same as x divided by y. And while we substitute those two terms, we still need to be able to represent what is the derivative of y with respect to x. So in order to find that, we'll actually want to rearrange this equation to get it equal to y equals. And then we'll take the derivative of that expression with respect to x, and that's what we'll substitute for the left side. So as we solve this first equation, multiply both sides by x, and we get y is equal to v times x. And then as we think about taking this derivative with respect to x, we need to remember that v depends on our independent variable x. So it's really the derivative of some function that's dependent upon x times x, which we'll use product rule for derivatives. So we get our dy dx equals the derivative of v with respect to x times the second term just left alone, plus, okay, our v term times the derivative of x with respect to x, which is just 1. So we'll get the simplified expression dy dx equals dv dx times x plus v. And this is what we'll substitute for the left side of the expression. Now, as we work to simplify after we made our substitutions, we see we have a v on both sides. We'll subtract v from both, they'll disappear. And we're left with the expression x times dv dx equals 1/2 v to the negative 1. So we've made our substitution. Now let's look at the resulting differential equation and think about what type of differential equation is it, so then we'll know how we could go about solving it. Since our terms are only involving multiplication, we could easily separate this and get all the terms involving v to the left side, all the terms involving x to the right side, and we'll be looking at a separable differential equation. So rearranging the expression, we get 2 times v times our dv dx is going to be equal to 1 over x. And now as we integrate both sides with respect to x, we will get v squared equals natural log absolute value of x plus c. And before we finish the problem, we just remember that v was representing our y over x squared. So this is y squared over x squared equals natural log of the absolute value of x plus c. We can isolate the y squared term, and we get y squared equals x squared times ln absolute value of x plus c is our answer. Now this next differential equation is neither linear nor separable, and particularly as we look at what's inside the square root, we can see that it works very well for a simple substitution. Let's let v be equal to x plus y plus 1. Now if we substitute that here, we'll get the square root of v. But in order to write the left side as a substitution, we need to find out what is y and then take its derivative, and that's what we'll substitute for the left side of y prime. So here we can isolate y in our v equals x plus y plus 1, as y is equal to v minus x minus 1. So dy dx, or y prime, is equal to dv dx minus 1, and then of course the derivative of minus 1 for the third term is just 0, because it's a constant. Now this will take the place of our y prime, and we can rewrite the original expression as dv dx minus 1 equals v to the 1/2 power. Add 1 to both sides. So we've identified a helpful substitution, we've substituted, we've simplified. Now we look at the resulting expression and think about what classification of differential equation it is so that we can go about solving the differential equation. I notice that if we think of this as one group, we could divide both sides by v to the 1/2 plus 1 and get all terms involving a v to one side, all terms involving an x to the other, which would put us as a separable differential equation. So we have 1 over v to the 1/2 plus 1 dv dx. All that would leave is 1 on the other side. And we can integrate both sides with respect to x. Now in order to integrate the left side, we'll need another substitution. If we let v be equal to u squared, then we get our dv term is 2u times du, and the left side, integrated with respect to x, will simplify to be the integral of 2u over, now u squared raised to the 1/2 power just simplifies to be u. So we have our u plus 1 with respect to u equals the integral of 1 with respect to x. We know the right side will integrate to x plus c, and as we're thinking about integrating the left side, we need to use long division to simplify what is 2u divided by u plus 1. Remember, long division should be used if the denominator's power is equal or greater than the numerator's power. So we set up our long division, 2u, our u plus 1, and we see if we multiply the u plus 1 by 2, we'll get this expression. When we subtract, those terms cancel and we're left with a negative 2 as the remainder. So the left side simplifies to be the integral of 2 with respect to u minus the integral of 2 over u plus 1 with respect to u, which is equal to the right side, which is just x plus c. Now we can integrate these both quickly. We get 2u minus 2 natural log absolute value of u plus 1. And now we begin the process of reversing our substitutions. We know that v is equal to u squared, or equivalently u is equal to v to the 1/2. So we get 2 times the square root of v minus 2 natural log. Now here the square root of v will always be positive, so we can drop the absolute values for our natural log here, x plus c. What was v? V started off as our original expression, x plus y plus 1, so we get 2 times the square root of x plus y plus 1 minus 2 natural log times the square root of x plus y plus 1, all plus 1, equals x plus c. And that will be our solution to the differential equation. The first thing we'll do with this expression is to divide both sides by x squared to simplify the term in front of the y prime. And we get y prime plus 2x over x squared, y equals 1 over x squared times 5 y to the 4th. We can simplify the left side And now we look at this simplified differential equation and think, what could we classify it as? And particularly, we see that we have our term where we've got y prime times some function of x times y equals some function of x times some term involving y to some power. And that makes us think of a Bernoulli differential equation, where our x squared times 5 is our q of x, some function in terms of x. Our 2 over x is playing the role of p of x. And once we recognize that we have a Bernoulli equation, then we have the substitution. V should be set equal to y to the 1 minus n, where n is the number that the y term is being raised to on the right side. So for our problem, we get v equals y to the 1 minus 4, which will give us that v equals y to the negative 3. Now, as we go through our substitutions, we know that we need to substitute not only for terms that are just y, but also y prime. So we're going to rewrite this substitution to get y by itself so that we can then take its derivative, and that will give us our y prime substitution. Now, as you're trying to simplify this, remember, negative exponents are just this, so we can simplify this to be y cubed equals 1 over v. As we get y by itself, we'll take the cube root of both sides. Y equals v to the negative 1/3 power. As we take the derivative, we see y prime should be 1/3 v to the negative 4/3 times the derivative of v with respect to x. Let's rewrite our equation with these substitutions. And now we will simplify. We get 1/3 v to the negative 4/3 times our derivative with respect to x of v plus 2 over x v to the negative 1/3 equals 5 over x squared. Exponent to exponents, remember you multiply the exponent, so we get v to the negative 4/3. We will want to divide both sides by this term to get our dv dx term isolated. So as we do that, we get dv dx plus 2 over x times v to the negative 1/3, all divided by 1/3 v to the negative 4/3, equals 5 over x squared times v to the negative 4/3, all divided by 1/3 v to the negative 4/3. Now, as I'm writing this, I realize there's one error we need to correct on signs. When you bring down the power of negative 1/3 as the derivative, this should have been negative 1/3, and let's make sure we follow that throughout. That should be negative 1/3, negative 1/3, negative 1/3, and negative 1/3. These terms cancel, and 1 divided by negative 1/3 is the same as just negative 3. So the right side simplifies to be negative 15 over x squared. And here we have negative 1/3 minus negative 4/3 is negative 1/3 plus 4/3. That just becomes 3/3 or 1, so we're left with a v to the first power on our second term on the left side. So we have 2 divided by negative 1/3 is negative 6 over x times v plus our dv dx. So we have made our substitutions and we've simplified the expression so that we can really see what we're looking at. And we now know at this step in the process we've made our substitutions, we've simplified, so we're going to need to try to classify this so that we know a proper solution strategy. Okay. First off, we classify what order is this differential equation. We see that we have the derivative, the first derivative only, so it's a first order differential equation. Furthermore, it's linear because all the terms involving v are to the first power, So we have v to the first power, the derivative to the first power. The terms are not being multiplied together. So this is a linear first-order differential equation. And once we've identified it's a linear first-order differential equation, we know that we'll solve this using our integrating factor method. So we first calculate our integrating factor. It is going to be e raised to this term, the term that's getting multiplied by just the v. So we have to the negative 6x dx. Now this is e to the negative 6 ln of x. But remember properties of logarithms, constant multiples are really exponents to the input. So this becomes e to the natural log x to the negative 6. E and natural log are inverse functions, so this will just simplify to our integrating factor being x to the negative 6. Now we'll both multiply both sides of the equation by our integrating factor x to the negative 6. And we'll get x to the negative 6 times dv dx plus negative 6 over x times x to the negative 6 times v equals negative 15 over x squared times x to the negative 6. And we can simplify these two terms. Okay, I'll just rewrite this as negative 6 x to the negative 7th times v equals negative 15 times x to the negative 8. Now once we multiply through by our integrating factor, we notice that the left side is of the form of the result of product rule, where we have our first term times the derivative of the second plus the derivative of the first term times the second. So as we integrate both sides with respect to x, since we know that what we're looking at on the left side is the result of product rule, integrating it just takes us back to the original product of functions that you were going to take the derivative of, which in this case is x to the negative 6 times v. So after we integrate with both sides with respect to x, okay. And as we integrate the right side, this is just simply integrating a polynomial. You know, you add 1 to the power and divide by it, so we get negative 15 over negative 7, x to the negative 7th plus c. And then we'll want to spend a bit of time simplifying and kind of cleaning up our solution. We know dividing negative by negative would make that positive. And then we will divide both sides by x to the negative 6th. But we also know dividing by x to the negative 6 is equivalent to multiplying by x to the 6th power. So that will give us v equals 15 over 7 x to the negative 7 times x to the positive 6 plus c times x to the positive 6th. So v equals 15 over 7 x to the negative 1 plus c x to the 6th, and I'll just rewrite this down in the denominator. Now we need to think about what was v, so we look back at our expression. V was originally y to the negative 3. So this is y to the negative 3rd power equals this side. And if I want to simplify this just to what y cubed would be, get rid of kind of the negative exponent, I know it would help me if I could rewrite the right side as a single fraction, because y to the negative 3rd is just 1 over y cubed. So if I can write the right side as a single fraction, then I could simply just kind of multiply both sides by y cubed, divide both sides by the right fraction, and we'll get what y cubed will be equal to. So to do that, we realize this fraction has 7 to the x, so we multiply by 7 to the x divided by 7 to the x. This is just 1. And we get the right side combined to a common denominator is 15 plus 7cx to the 7th, all over 7. And then we find that y cubed, we just take the reciprocal of both sides, and we get 7x over 15 plus 7c x to the 7th. Looking at this differential equation, we notice that it's a slightly different format than we're used to seeing. We have our dx and our dy term. This is called the differential form. And it's important to note that we could rewrite this if we wanted to in the equivalent format of this. So these equations are the same, they just differ in formatting. And as we're looking at this, we might want to try to see if this is an exact equation. And we know to do that, we're going to take the coefficients, where this is our function, m as a function of x and y. We have n as a function of x and y. And to verify if we're exact, we need to see if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. If that's true, our equation is exact. So let's find the partial of m with respect to y. So here, our first term, 4x, doesn't involve y at all, so we know its derivative with respect to y is 0, so we have our 0, minus the derivative of y is just negative 1. Our partial of n with respect to x, the first term, 6y, doesn't involve an x, so its derivative is 0, minus the derivative of x with respect to x is negative 1. These are the same, so we know we're dealing with an exact equation. Now, if we're dealing with an exact equation, then we know our solution to our differential equation f, which is a function of x comma y, has the following properties. We know that if we took the derivative of f with respect to x, that's what would give us our m term. Similarly, if we took the partial derivative of f with respect to y, that's what will give us our n. So using that, we can actually figure out and determine what the solution, capital F, a function of x and y, is for this differential equation. So using this, if we integrate our m, our 4x minus y, with respect to x, since it is the partial derivative with respect to x, we're going to get back what our function capital of f of x looks like. So f of x comma y, our first term integrating that with respect to x would give us 2x squared minus, now our term y would give us an xy. And then we need to remember that if we were taking the derivative of this with respect to x, any term that was solely in terms of y would disappear when you take its derivative to 0, which is why we need to write some kind of function solely in terms of y. So we can say plus some h of y. And this is just saying this piece only involves y. And we're almost to our solution. We just need to figure out what is this, and then we'll have our solution to the differential equation. So the way we'll go about finding what is this term solely in terms of y is it said if this is our capital F, then if we took the derivative of this with respect to y, we should get this back as a result. So let's take the derivative of f with respect to y. Now this first term is only in terms of x, so its derivative is 0. Minus, okay, this derivative with respect to y would just be negative x plus h prime of y. Now this needs to be equal to n based on our result of this being an exact equation. So we see I have our minus x here, which tells us that the derivative of our term only involving y is 6y. So h prime of y is 6y. Integrating that, we get our function h of y was 3y squared. And with that, we can substitute that into our capital F of x function. Capital F of x comma y. So our implicit solution for this exact equation is an arbitrary constant equals 2x squared minus xy plus 3y squared. Now, as we look at this next differential equation, we see that we have a second derivative listed. So this is a second order differential equation, and we have the second derivative of y, we have the first derivative of y, but one thing that we note is that the term y itself is missing from the differential equation, and this will indicate a helpful substitution. p equal to y prime. And by using this substitution, we will be able to turn what was a second-order differential equation into a first-order differential equation. So if p is equal to y prime, then p prime is equal to y double prime. And our differential equation would become x times p prime plus p equals 4x. So we've applied our substitution. Let's take a moment and just look at this equation and try to think through some solution strategies. Particularly look at some patterns involved on the left side of the equal sign. This is exactly the result of taking the derivative with respect to x of x times p. Because we have the derivative of x is 1 times p plus x times the derivative of p. In that case, since we are recognizing the left side is the result of product rule, when we integrate both sides with respect to x, we'll just get back the original product, and then the integrating the right side with respect to x should give us 2x squared plus c. Divide both sides by p, and we get p equals 2x plus c times x to the negative 1. And now remember what p was equal to. It was y prime. So we have y prime equals 2x plus c x to the negative 1. And in order to solve this, we see that we could integrate both sides. And at this point, since we're going to integrate again, that's going to create another arbitrary constant. So we might call this c1. Our next constant will be c2, or you can also use the capital alphabetical letters a, b, c. So let's integrate both sides again with respect to x, and we get the function y is x squared plus our c1 times the integral of x to the negative 1 is ln absolute value of x, plus our second arbitrary constant c2. We see we're looking at a second order differential equation. And again, it just has the terms y prime, y double prime. So if we make the substitution p equals y prime, and then our p prime would equal y double prime, we'll get the first order differential equation of p prime equals x plus p squared. And to simplify the interior of the square, we can use another substitution. Let's let v be equal to x plus p. So that will substitute here. But we also need to find a substitution in terms of v for p prime. So let's solve this equation to get p by itself. P is equal to v minus x. So the derivative of p is equal to the derivative of v minus 1. All in terms of x, the derivative in terms of x. So we have our equation simplifies to v prime minus 1 equals v squared. When we add 1 to both sides, we see we're looking at now a separable differential equation. And as we integrate both sides with respect to x, we'll get inverse tangent of v is equal to x plus our constant, let's call that a. Now, if we have tangent of inverse tangent of v, that will simplify to just be v, but that would involve taking tangent of the right side. And now let's simplify what was v representing. It was x plus p. We can subtract x from both sides and we get p but we recall that all along p was y prime. So y prime, the derivative of y with respect to x is this. So I could find the solution y by integrating both sides with respect to x. That'll give me y equals Now here we'll need to recall back from Calc 2, the integral of tangent, especially our interior x plus a, even though we might use a u substitution, we know if we let u equal x plus a, du is just dx, so this will simplify. So the integral of tangent is natural log, the absolute value of secant, of our x plus a. So we have natural log absolute value secant of x plus a minus 1/2 x squared. Since we integrated again, we have our second constant plus constant b.